the minimum cost, we have that. Now how can we get the partial P, partial Fij? Now the only equation we have for P is the following. That's the equation we have. We have that long equation. If you don't look at a partial sign there, that's the equation we have. Now, so to get partial P, partial Fij, then you gotta look at the equation we have for the P. So that is whatever we have here. Now partial P AC plus BCFC parentheses transpose, then partial P partial Fij, then minus partial P partial Fij, then parentheses AC plus BCFC, now equal to this. Now that has P and this one get F, then that's partial F T partial C partial Fij, and we have that term plus FCR plus PBC parentheses partial FC partial Fij. So you need to look at back the definition for FC, the equation for FC. And if you look at that, then we know that partial P partial Fij equals 0. That means that equals 0, that equals 0 implies that this BFC plus BC transpose P equals 0. You know why? Because that one is, there's some value there, at least for each element there's a 1 inside. FC, did you know that FC is the matrix for the Fij. So this term will be 0, and that term will be 0 because you have the n term minimum, n times m terms here, and n times m terms here. But if this equals 0, this equals 0, this won't be equal to 0, this won't be equal to 0, that means that has to be equal to 0. That means FC equal to minus R inverse BC transpose P. Now there's the inverse here. See that? That's why R is required to be positive definite. That means R cannot be 0. R cannot, the inverse must be exist. Now if R is positive definite, then the inverse is exist. The inverse exists because we require that R must be positive definite. So that's R inverse exists. So that's the solution. So FC equal to minus R inverse BCTP. So from this equation, from that equation require FC, again equal to minus R inverse B C transpose and B and P. Okay, now we got this kind of important equations. Now when we sub FC in, that must be invertible. When we insert FC into that equations, we insert FC into that equations, then we call Ricardo equation into that here. So that is the optimum control. This is the equation to solve the P, and because you solve the P means you solve the F. So that's we call Ricardo equations. The Ricardo equation is the equation that require for the optimum control to solve the optimal control gain. If you look at carefully this, you can see that there's a linear term here, there's a linear term here, there's a quadratic term here, PP, quadratic terms. So that quadratic term equivalent to either in the single degree freedoms, then that means the two roots. You put out two roots. If you look at this, if AC is a scalar, just AC is scalar, and this P will be scalar, and then if R is a scalar and Q is scalar, then this is just nothing but a second order algebraic equations. All right, so that is the Ricardo equations. Now there's a problem exists. in the MATLAB or inside it to solve this. That's the easy way to do it. You don't have to really solve it by hand. No, that problem exists about 20 or 30 years ago. Some people know how to solve this. It's easy to solve in terms of the programming. All right. Now we got the equation. That's the equation, the most important equation for the optimal control. That's the equation you have to solve to get P. And if you get P, then you got R. Any questions about this? All right. I did not. I don't want to spend too much time to explain the whole detail of these derivations, because this derivation is nothing but just to look at this each term of P, partial Fij. I is from one to number of inputs, and J is from one to number of states. Number of states is N, for example, and then you will get these equations. Now, if you read a different book, they give you a different way to divide it. This is the way I like to see that divided, because this is don't get involved too much in the metric fit. Again, still involve some of those. All right, formulation, control gain. Control gain, now we know that. Control gain FC equal to minus R inverse BC transpose P. And that P is solved by the Riccati equations. That's this. And that Riccati equation gives P must be larger than 0. That means P must be positive definite. All right? And this is the solution is unique because P has to be positive definite. That means it's only a solution there. And control force. And this is the control force. U equal to FCX equal to minus R inverse BC transpose PX. So this is your control force. Again, if you look at this, when R going to infinity, R very large, then we know that U will be very small. From this equation is, you can see that. So U is is reverse, is the inverse of the of R. So R, when R is large, then U becomes small. And you can see from here. All right, example. Now look at this example. That's the example I show you about 2 hours ago. And if you look at this, then we start into the Riccati equations. Then we got this. This is exactly the same as you got earlier. All right. Then solution P is this. But now P has to be positive. All right. A, well, this is two solutions. If A is smaller than 0, when A less than 0, the constant P on the control gain F becomes this. All right. So because A less than 0 and this has to be, P has to be positive. All right. This P has to be positive. And if you look at A is negative, A is here. And so if A is negative, B squared is positive, and R is positive, and so this one has to be negative. So 1 minus this, inside this is negative. So negative times negative, P is positive. True? Now, if you take positive term here, if you say add here, if positive here, then P becomes negative because A is negative. True? Yes. So you don't have to use the way I proved it. Say P it has to be unique because P has to be positive. If P is positive, then only way P is positive is plus or minus sign, sign has to be negative. So that's the solutions. Now, this under the condition A is negative. Now, if A is positive, then if A is positive, then the positive sign will be the one to use. Okay? So if A is negative, then negative sign is the way to use it. So this solution depends on A is positive or negative. For stable system, then negative is the one to use. For unstable system, positive is the one to use it. Or for, if you look at this, if P is, has to be positive values. Okay, so when R going to infinitive, then this becomes 0. Then 1 minus 1 equals 0. Okay. Now A plus BF doesn't always hold for A negative because BF doesn't 0. Alright, that's if you look at this, B is positive, P is positive, R is positive, so F is negative. True? Okay, if F is always negative, if from this, you look at from this way. Okay, that's the example. This exact example is the same example as I use when I begin the optimal control class. Then look at the airplane example. This is another example. It's 2 different films. I'm just showing you some of the example. Psi is perturbation from cruise angle of attack. Phi is perturbation of cruise path, pitch, angular velocity. I don't spend too much time here. And tau is that's a lifting time constant. Omega is undamped pitch natural frequency. N is the elevator diffractions. That's how the when it's sitting in the aircraft, in the airplane, this is the way they control. Or if they use optimal control. Alright. Now what we want to do is determine the steady state constant gains F1 and F2 such that U equal to F1 psi and plus F2 phi. Alright? Now, to minimize, that's the index I'm using. The index is psi square plus phi square plus U square parenthesis dt. Now, from here, how much is R? 1. And how much is U? So, how much is the Q? The weighting. And we can see the next. So, that's the equation of motion. That's the equation become like that. And so we have AC, BC, and R equal to 1, QC equal to 1, 0, 0, 1, right?